Well, thanks everyone. I'm really disappointed to not be able to join you in person this week. But good news, we're out at Maxar this week taking some great image tests with the Heimdall cameras and the sampler arm that are going to be co-manifested with Lunar Vise. And so we are really excited to be doing these activities. So today I'm going to tell you about the PITMS, the Peregrine Ion Trap Mass Spectrometer. We flew at the beginning of last year, and I'm going to tell you about some of the results. Just to set you up, we have a couple published papers that I'll show you at the end. So if you want the instrument details and all the nitty gritty, you can go to those publications. But just real quick, PITMS is a mass spectrometer. It's an ion trap mass spectrometer. Atoms go into the top of the mass spectrometer, as you see in the middle here. They sort of circulate around the ion trap. They get trapped and ejected in order of mass. We build up a mass spectrometer that way. PITMS was a really successful partnership between NASA and ESA. The mass spectrometer itself was built in the United Kingdom. The wrapper around it was built in the US. We had a very successful partnership that we're very proud of. Next slide. And we were at a lunar payloads call, NASA lunar payloads call, and we were manifested on the Astrobotic lander. Let's skip by this one, thanks. Next slide. So the Peregrine mission, many of you in the room are familiar with this. This is the way it was supposed to go. Next slide. Next slide is the way it actually went. So we were supposed to have, a landing on the moon. That's what we were all geared up for. We had a propulsion anomaly shortly after launch, so we had 10 days in space where we were able to turn all of the instruments on and to get data in cislunar space. That's not what PITMS was designed for, but the results that we got from those data not only showed the performance of PITMS, but actually showed some really interesting data about the spacecraft, and that's what I want to talk to you today about. The anomaly that we caused us not to land on the moon was a propulsion leak, an oxidizer leak. So as the propulsion system was being pressurized, the helium valve didn't close, and so the oxidizer tank overpressurized and burst a leak. So we lost all of our oxidizer, or much of our oxidizer, vented into space. And so that's something that PITMS can and did detect. So we have some information on the leak that we detected and then about the outgassing in general of the spacecraft. So next slide. Let's dive into next slide, please. I thought I had 15 minutes, so sorry. I'm going to blow through these beginning slides because I really want to show you these results. Like I said, there's papers where you can look up the rest of it. So here's the PITMS performance. Like I said, we were able to turn on, we had about 8 hours of data over 4 different sessions. The mass spectra that you can see here, they're really well-formed, sharp peaks. The noise level is fairly low. This was a really, really nice instrument. It would have been really great to get on the moon. The instrument itself is being built upon, and new versions of PITMS are going to be flying on LUPEX and on the Prospect payload, both by ESA. So and the mass spectrometer will have another life on the moon, we hope. We did a very rigorous calibration process despite, not landing on the moon. That calibration process can be applied to all of our next generation data, and all of our data are archived in the PDS. On our PDS users guide, by the way, if anyone wants this, the PDS users guide has a really detailed discussion of things like artifacts and ghost peaks and count limiting and all the things that you'd expect from mass spectrometers. Next slide. Okay, so here are the measurements that we took. So like I said, we turned on in 4 different sessions throughout the 10 days that we were in space. On the bottom there is mission elapsed time in hours. So those are the 4 sessions where we were able to turn on and operate. So we didn't turn on until about 4 days after launch. The way that PITMS worked is we had a dust cover over the aperture so that when we landed, the aperture is looking to zenith, and we didn't want dust coming from the landing into the aperture. So we had a dust cover, but it wasn't a seal. So it was not hermetically sealed. In fact, it was deliberately not to allow gases to equilibrate and to keep the dust out. We did want to do some experiments in cislunar space with that equilibration of the gas in cislunar space. So this turned out to be something that was validating that approach. So the first time we turned on the mass spectrometer, there's a lot of residual water that had absorbed onto the mass spectrometer, onto the filament, and indeed onto the spacecraft, as we'll see, just during its time on Earth. The lander itself and the instruments were kept in a clean room much, but not all of the time on the Earth. So as it was being transported between clean rooms, as it was environmentally tested, it was outside of the clean room environment, and so it was adsorbing terrestrial atmosphere. So when we first turned on the mass spectrometer there, that first point on the left, that's a lot of water outgassing. So you can see the total instrument pressure is on the y-axis. So that's all of the ions put together to give you the total pressure inside the instrument. And that is 10 to the minus 6 millibar. So that's a pretty high pressure reading. That's well outside of our design specification. We did not expect to find 10 to the minus 6 millibar of anything on the surface of the moon. So that's well outside of our design specification. There's some caveats associated with that total pressure because it's so far outside of design spec. But that's to be expected, that there was water kind of off-gassing from the mass spectrometer. The next time we turned it on, you can see in the middle of the graph, there's a dotted line there. That dotted line represents when we opened our dust cover. So we took some spectra just before opening. Those are the orange diamonds there. And then we took some more spectra after opening the dust cover in the same session. And those are those blue circles. So the water, or the total pressure came down from the first session, so we probably outgassed a lot of our materials. And then when we opened the dust cover and equilibrated with the spacecraft environment, you can see that the total pressure dropped to about 2 times 10 to the minus 6 millibar. So that's equilibration outside of the PITMS box itself. And then when we turn on for the third and fourth times, those circles are kind of overlapping there, those blue circles. It stayed constant. So we're measuring the spacecraft background at that point until the end of the PITMS measurements. And then, of course, shortly after that, the re-entry into Earth's atmosphere. So next slide, please. So that's roughly what we were looking at with PITMS over the course of the mission. So then we wanted to work out, well, we have the mass spectra. What are we seeing in the mass spectra? So to work out the abundances that we saw in the mass spectra, here's on the top there is what you can see. The blue line there is what the mass spectrometer saw with the dust cover closed. So that's an actual mass spectrum, calibrated mass spectrum. And then that white line is one of our models. We ran a couple hundred just least squares fit models using inputs of individual species that may be there, that maybe were expected to be there, a whole bunch of different components that we thought could be in the mix. And then the bottom spectrum there is the NIST standard spectrum for, this is, I think, for nitrogen dioxide. So the propulsion system was nitrogen tetroxide plus nitrogen oxide, so MON 25% nitrogen oxide in dinitrogen tetroxide and 2O4. And then that mixes with the oxidizer and hydrazine, with the fuel, and causes the propulsion to go. So we tried to look at all the different components of the propulsion system, what could be in there, terrestrial atmosphere, things that could be clinging on, things that could be outgassing from the spacecraft. We put in all of the NIST standard spectra for the way that these break down under electron impact. So the point here is that nitrogen dioxide is not just one spectral line, it's a collection of spectral lines as that molecule breaks up under electron impact, which is what we're doing to it. So we convolve that NIST standard spectrum with the PITMS response function, which causes the broadening. And then we mix those together with, like I said, a least squares fit until we can fit our spectrum. And then that's how we pull out the fingerprint of what was in the mix to cause the spectrum that we see. And so these abundances are maybe not, to 8 decimal places correct, but it's going to give you an idea of what we saw. And then we used combinations as well. What's in the terrestrial atmosphere, what's in the byproducts of combustion, the MON25 oxidizer, the MMH itself. So next slide. The next 2 slides, I'm going to show you what we saw with the dust cover open and what we saw with the dust cover closed. So first, the dust cover closed.
You have 1 minute, thanks.
Yeah, thanks. So first, the dust cover closed. This is the best fit. It's about 60% water and about 33% oxidizer. Not unexpected. It was a big oxidizer leak. Uncombusted fuel, combustion, a little bit there, no terrestrial atmosphere detected. Next slide, with the dust cover open, you saw that big pressure drop. Next slide, please. Oh, thank you. That's good. Dust cover open. Sorry. You saw the big pressure drop, but actually the species detected didn't change at all. So it's the same species, mostly water, some oxidizer, and some uncombusted and combusted fuel. So that's what we saw. Next slide is going to be spacecraft outgassing or off-gassing. Huge amount of off-gassing. Like I said, that 10 to the minus 6 millibars of pressure, that's a lot compared to other spacecraft. Again, this is something that we're going to need to work through with commercial landers, where they may not be as clean as what we're expecting from NASA missions. I don't mean that in a slam. I don't mean that to say that everyone's dirty. It just means that there was a lot of off-gassing. And that's something that we're going to need to deal with, especially things like mass spectrometers or things like lenses that may be cold that may get iced up. And the next slide, I think, is going to be the last one. So we also modeled how that oxidizer moved around the lander, that's a whole separate paper that's about to come out. So the oxidizer jetted out into space, but it also moved through the lander surfaces and under the MLI, and that's how it got to PITMS for us to be able to detect it. So that was a really interesting outcome of our study as well. So next slide is the last slide with some conclusions. Again, we've published 3 papers on this, and our data are all in the PDS. We were really excited to fly with Astrobotic. We thank everyone for a super wild ride, and I'll be around at the end of the session for questions. So thank you for your attention.